Hello students, now we move to the next section, accumulation point of a set in a topological space. Accumulation point is same as limit points. So let capital A be a subset of a topological space. A point y is said to be, suppose we have a topological space X2 and we have a subset capital A. Okay, and any point y, that may be inside or outside, y is said to be a limit point, that is said to be a limit point of capital A if we consider any open set containing y that must contain points of capital A other than y. At least they have at least one point common. For any open set containing y contains at least one point of capital A other than y. And this is the definition of accumulation point or limit point. Okay, let's see some examples. Consider real line with the usual topology. To you, that is usual topology. Take capital A equal to open interval 0, 1. Okay, then what is the limit point of interval 0, 1? And you can see that 0 is clearly a limit point of the interval 0, 1. Why? Because if we consider any open set containing 0 in real line with the usual topology, any open set containing 0 in usual topology, it is of the form open interval containing 0. Therefore, it must intersect capital A equal to open interval 0, 1 with at least one point. At least one point. Therefore, 0 is a limit point of capital A, 1 is again limit point of capital A, and any point between 0 and 1 is again a limit point of capital A. Therefore, the set of all points in between 0 and 1, both 0 and 1 are limit points of capital A. And the set of all limit points of capital A is called a derived set, and which is denoted by A prime. So in this case, A prime is nothing but all the points in between 0 and 1 and both the points closed 0 and 1. Therefore, it will be closed interval 0, 1. Therefore, closed interval 0, 1 will be the derived set of open interval 0, 1 in usual space. One more example. Consider any set capital X together with a discrete topology. That may be real line, or any set together with a discrete topology. Now let A be a set which is non-empty set. A be a non-empty set. Okay. Then if y is a limit point, I consider if y is a limit point of capital A, then by definition every open set containing y must intersect capital A other than one point, the central point y. Okay, so let v equal to singleton set to y. Okay, then v is open in X with the tau dy, because in discrete topology every set is open, in particular singleton set is open. Therefore, singleton y will be open sets. Then what is v intersection A? V intersection A is nothing but singleton set y intersection capital A. Okay, that is equal to, അപ്പോൾ ഈ രണ്ട് സെറ്റിൻ്റെ intersection എന്ന് പറയുന്നത് that may be either y or empty. If y belongs to capital A, then their intersection is y itself. If y not belongs to capital A, then it must be empty set. So, the open set V cannot intersect the set capital A with one point. So it is, their intersection is actually empty, corresponding to this A. Therefore, y cannot be a limit point. Y cannot be a limit point. So since y is arbitrary, no point can be a limit point of capital A with respect to discrete topology. No point, I will write here, no point can be a limit point of capital A in discrete space. So subsets of discrete space. Any set in the discrete space cannot have limit points because their singletons are open. Therefore, singletons cannot intersect with any set with other than the point. Okay, so it has no limit points. Now what is the case of indiscrete space? Now we consider another example, x with the indiscrete space. In discrete space, the open sets are phi and x only. So let A be any subset of capital X. A point, suppose A is equal to some singleton set to Y. Then A cannot have a limit point. Why? Any set, if we consider any open set containing the point Y, okay, we consider, let Y be a limit point of A. Then you consider any open set containing Y. Here the only open sets are empty set and X itself. So any open set containing Y will be capital X. Therefore, capital X is the only open set containing Y. Then X can contain all points of capital A. If capital A is singleton set Y, it cannot have a limit point. Otherwise, all points of capital A will be limit points of capital A in indiscrete topological space. Okay. Now we have a theorem. Let capital A be a subset of a topological space X tau, then A closure equal to A union A prime, which is already discussed in real analysis class metric spaces. E closure is equal to E union E prime. So here we are going to prove this statement, A closure is equal to A union A prime. Okay. So let's see how to prove this. So we have to prove that A closure is equal to A union A prime. So first we prove A closure is contained in A union A prime and A union A prime is contained in A closure. Okay. First we prove that A union A prime is contained in A closure. We know that A is always contained in A closure. For any set is contained in its closure, therefore A is contained in A closure. Now we need only prove that A prime is contained in A closure. If we prove A prime is contained in A closure, then A union A prime will be contained in A closure. So now we prove A prime is contained in A closure. Okay, so let X belongs to A prime. We take a point in A prime. We have to prove that that point is also belongs to A closure. So let X be a point in A prime. We have to prove that X belongs to A closure. Okay, so assume the contrary. If possible, X cannot be belongs to A closure. If X cannot be belongs to A closure means X belongs to A closure complement, that is X minus A closure. X A closure ഇല്ലെങ്കിൽ പിന്നെ അത് എവിടെയായിരിക്കും? A closureന്റെ കോംപ്ലിമെൻറ്റിലായിരിക്കും. കോംപ്ലിമെൻ്റ് ആണ് X minus A closure എന്ന് എഴുതുന്നത്. Ready? So if X cannot be belongs to A closure, then X belongs to X minus A closure. Okay, since now we know that closure of a set is always closed. We have a closure is always closed. Always closed. Therefore, since a closure is closed, its complement is open. What is its complement? X minus a closure is always open. X minus a closure is always open. Also, we have X is not belongs to a closure and X belongs to X minus a closure. So I can say that X minus a closure is an open set and contain the point X. Open set containing X. Containing X. So X minus a closure is an open set containing the point small x. Okay. Now, if we consider any set capital A will be always contained in A closure. Suppose this is our universal set U and this is A and this is suppose A closure. Then X minus A closure, suppose this is capital X, okay. Then what is X minus A closure? This shaded portion is capital A and the whole thing will be equal to A closure and the outside portion of this will be X minus A closure. So you can easily see that the intersection of any set capital A and X minus A closure will be empty. Okay, A intersection X minus A closure. A deyum X minus A closure deyum intersection, that will be always empty. A intersection X minus A closure will be empty for any set A. Clear avunnando? For any set A. Okay, now what is X minus A closure? X minus A closure is an open set containing X. So X minus A closure is an open set containing X and intersection with capital A equal to empty. Which means the point X cannot be a limit point of capital A. എന്തുകൊണ്ടാണ്? Since if X is a limit point of capital A, then by the definition, every open set of small x have to intersect with the capital A. Clear? Clear? Here, X minus A closure is an open set containing X, but it cannot intersect with the capital A. Their intersection is empty. അപ്പോൾ ഇവർ രണ്ടുപേരുടെ ഇൻ്റർസെക്ഷൻ എം ടി ആണെന്ന് പറഞ്ഞാൽ ഇത് എക്സിനെ കണ്ടെയ്ൻ ചെയ്യുന്ന ഓപ്പൺ സെറ്റ് ആണ്. അപ്പോൾ എക്സ് എന്താവാൻ പറ്റില്ല? ലിമിറ്റ് പോയിന്റ് ആവാൻ പറ്റില്ല. എക്സ് എയുടെ ലിമിറ്റ് പോയിന്റ് ആയിരുന്നുവെങ്കിൽ ഇഫ് എക്സ് ഇസ് എ ലിമിറ്റ് പോയിന്റ് ഓഫ് ക്യാപിറ്റൽ എ ദെയർ ഇൻ്റർസെക്ഷൻ മസ്റ്റ് ബി നോൺ എം ടി. Ready? Non-empty. Here x minus a closure cannot be intersect with capital A. Therefore, the point x cannot be a limit point of capital A. Since x is not a limit point of capital A, x cannot be belongs to A prime. Why? If x is a limit point of capital A, x must be belongs to A prime because A prime is the derived set. It contains all of its limit points. Therefore, x cannot be belongs to A prime. So, what we'll get? Whenever x belongs to here, whenever x not belongs to A closure, we get x not belongs to A prime. That is, we prove x not belongs to A closure implies x not belongs to A prime. But which is a contradiction. We already assumed that x belongs to A prime. We have to prove that x belongs to A closure. We assumed the contrary part, x cannot be belongs to A closure. Then, so we need a absurd result, that is we get x belongs to A prime, which is not possible because already chosen as x belongs to A prime. Ready? So, which implies x must be belongs to A closure. Therefore, x must be belongs to A closure means A prime is contained in A closure. A prime is contained in A closure. So, we get A is always contained in A closure. A prime is also contained in A closure. Therefore, A union A prime is contained in A closure. A union A prime is contained in A closure. Okay, so we get A union A prime is contained in A closure. Now, what we have to prove? We have to prove that A closure equal to A union A prime. So for that, I prove A union A prime is a closed set. We have A is always contained in A union A prime. This is true, right? A will be always contained in A union A prime. This is true for any set. Okay. If we prove A union A prime is a closed set, this is an assumption. If we prove A union A prime is a closed set, okay, then assume that this is proved. Then A union A prime is a closed set containing capital A. If we prove A union A prime is a closed set, then A union A prime is a closed set containing A. And we know that the smallest closed set, and we know that A closure is the smallest closed set containing A. We know A closure is the smallest closed set containing A. A ne contain ചെയ്യുന്നതിൽ ഏറ്റവും ചെറിയ closed set ഏതാണ്? A closure ആണ്. A closure is the smallest closed set containing A. So we have two closed sets, A union A prime and A closure. Both are containing capital A. And A closure is the smallest one. Therefore, which together implies A closure is the smallest closed set ആണ്. Therefore, A closure will be contained in A union A prime. So, this will be equation number 2. A union A prime and A closure are the two closed set containing A, and A closure is the smallest closed set such that which containing A. Therefore, smallest closed set containing A. Therefore, A closure will be contained in A union A prime. A closure A union A prime A ne contain ചെയ്യുന്നുണ്ട്. രണ്ടുപേരും ക്ലോസ്ഡ് ആണ്. അതിൽ ഏറ്റവും ചെറുത് A closure ആണ്. അതുകൊണ്ടാണ് A closure എന്താവുന്നത്. Therefore, A closure will be contained in A union A prime. This is equation number 2. For equation number 1, A union A prime contained in A closure. Equation number 2, A closure is contained in A union A prime. So, which together implies A closure will be equal to A union A prime. But we have to prove that A union A prime is a closed set. This is our subclaim. ഇത് പ്രൂവ് ചെയ്തെങ്കിൽ മാത്രമേ this will be true ആവത്തുള്ളൂ. മനസ്സിലാവുന്നുണ്ടോ? So we need only prove that A union A prime is a closed set. Okay? ഇത് പ്രൂവ് ചെയ്തെങ്കിൽ എന്ന് പറഞ്ഞിട്ടാണ് ഞാൻ കംപ്ലീറ്റ് ചെയ്തത്. Now we need only prove that A union A prime is a closed set. So our subclaim, A union A prime is a closed set. Is a closed set. So, to prove A union A prime is a closed set, we need only prove that its complement is open. It is enough to prove its complement. Its complement is x minus A union A prime is open. So, how can you prove that a set is open in topological space? A set is open if and only if it is neighborhood of each of its points. So to prove this set x minus A union A prime is open, we prove x minus A union A prime is a neighborhood of each of its points. Clear? So I take a point belongs to this set and I will prove that this set is a neighborhood of that point. So for that, let y belongs to x minus A union A prime. Okay. So which implies y belongs to x minus A union A prime means y belongs to x and y not belongs to A union A prime. So which implies y belongs to x and y not in A and y not in B. Not in A prime. Not belongs to A union B means not belongs to A and not belongs to B. Here not belongs to A and not belongs to A prime. Okay. Now consider this. Since y not belongs to A prime means, what is the meaning of y not belongs to A prime? Y not belongs to its derived set. Y not belongs to derived set means it is not a limit point. Y is not a limit point of capital A. Y is not a limit point means if y is a limit point of capital A, then by definition every open set containing y will intersect with the capital A other than the point y. So which is not a limit point means we have to apply the negation statement of our definition. So for every open set means, which implies by the negation statement of the definition, there exists an open set. There exists an open set V of small y such that V intersection capital A equal to empty or V intersection capital A equal to singleton set to Y. This is actually the negation statement of limit point. For every open set V of Y, their intersection must be non-empty or the point other than Y. Here, the negation, there exists an open set V of Y such that their intersection is either empty or their intersection is the only point, the central point Y. Okay. But we have y is not belongs to capital A. But we have y is not belongs to capital A. Since y not belongs to A, therefore their intersection cannot be equal to singleton set to Y. But we have y is not belongs to capital A, therefore y not belongs to capital A means their intersection V intersection A y ആവണമെങ്കിൽ ഈ y ഇതിനകത്തും വരണ്ടേ. V intersection A equal to y means y must be belongs to both V and A, but we have y not in A, therefore this intersection is not possible. Therefore V intersection A equal to y is not possible. So only possibility is V intersection A equal to empty. Therefore, I can write V intersection capital A equal to empty. Since V intersection capital A equal to empty implies V intersection A prime is also equal to empty. ഇവ തമ്മിലുള്ള ഇൻ്റർസെക്ഷൻ എം ടി ആണെങ്കിൽ തീർച്ചയായിട്ടും ആ സെറ്റും അതിൻ്റെ ഡിറൈവ്ഡ് സെറ്റും തമ്മിലുള്ള ഇൻ്റർസെക്ഷനും എം ടി ആയിരിക്കും. ഹൗ ദിസ് ഈസ് പോസിബിൾ? If we take a point, suppose Z is a point belongs to A prime intersection V, this intersection. So what will happen? Which implies Z belongs to A prime and Z belongs to V. Okay, Z belongs to A prime means Z is a limit point of capital A. Z is a limit point of capital A and Z belongs to V. What is this V? V is an open set. V is an open set. So V is an open set containing Z and Z is a limit point of capital A implies, what's the definition? If Z is a limit point of capital A, every open set must intersect with the capital A. Therefore, the open set V must intersect with the capital A. Therefore, V intersection A must be not equal to empty. ഇവർ തമ്മിൽ ഇൻ്റർസെക്റ്റ് ചെയ്യേണ്ടി വരും. വി സെഡിനെ കണ്ടെയ്ൻ ചെയ്യുന്ന ഓപ്പൺ സെറ്റ് ആണ്, സെഡ് എയുടെ ലിമിറ്റ് പോയിന്റ് ആണ്. അങ്ങനെയാണെങ്കിൽ വിയും എയും ഇൻ്റർസെക്റ്റ് ചെയ്യേണ്ടി വരും സെഡ് അല്ലാത്ത മറ്റൊരു പോയിന്റിൽ. പക്ഷേ ഇവിടെ എന്താ പറഞ്ഞിരിക്കുന്നത്? ബട്ട് ദിസ് ഈസ് നോട്ട് പോസിബിൾ സിൻസ് വി ഇൻ്റർസെക്ഷൻ എ ഈക്വൽ ടു empty. Therefore, no set can belong to A prime intersection V. That means V intersection A prime or A prime intersection V must be empty. Clear? Which together implies V intersection A empty, V intersection A prime empty. So I can write V intersection A union A prime is equal to empty. Okay, V intersection A union A prime is equal to empty. So to A intersection, what is the meaning of A intersection B equal to empty? A intersection B equal to empty means A is contained in X minus B or B is contained in X minus A. This is the meaning. A intersection B equal to empty implies either A is contained in X minus B or B is contained in X minus A. ഒന്ന് മറ്റൊന്നിൻ്റെ കോംപ്ലിമെൻറ്റിൽ കിടക്കുമ്പോഴാണ് രണ്ടുപേർ ഇൻ്റർസെക്ഷൻ എംറ്റി ആവുന്നത്. So by the same meaning, V intersection A union A prime is equal to empty means V is contained in there its complement. B complement. What is its complement? X minus A union A prime. So V is contained in X minus A union A prime. What is V? What is V? V is an open set containing Y. So which implies Y belongs to capital V and that V is contained in A union A prime. So we begin with let Y belongs to X minus A union A prime. Y belongs to X minus A union A prime and that Y is contained in V and that V is contained in X minus A union A prime and this V is open. What is the meaning of this statement? In between a point and a set, there is a open set to V, which implies X minus A union A prime is a neighborhood of Y, which implies X minus A union A prime is a neighborhood of each of its points because Y is arbitrary, each of its points, since Y is arbitrary. So which implies X minus A union A prime is open, which implies A union A prime is closed, its complement is closed. So that's about our subclaim, A union A prime is closed, which is an important theorem. So hence the proof.